On March 6, 1943, at Republic Aviation's airfield in Farmingdale, New York, test crews assembled around a silver prototype. The aircraft bore the designation XP-47B. Its fuselage was large and cylindrical, unlike any pursuit plane built before. The ground temperature measured 41 degrees Fahrenheit. Winds from the northwest moved at 7 miles per hour. Technicians in leather jackets adjusted the cowling of an experimental power plant, the Pratt Whitney R2800 double Wasp. The radial engine had 18 cylinders arranged in 2 rows. Each cylinder displaced 152 cubic inches. Total displacement measured 2,804 cubic inches. Rated output exceeded 2,000 horsepower. Observers from the U.S. Army Air Forces noted the unusual proportions. The aircraft stood over 14 feet high. Fully fueled, it weighed more than 7 tons. The design appeared excessive for a single-seat fighter. Yet Republic's engineers insisted the aircraft could climb, dive, and fight effectively above 30,000 feet. At 10:12 a.m., the double Wasp started. Its 13-foot propeller rotated slowly, then accelerated with a steady metallic rhythm. Air-cooled cylinders glowed faintly under load. Exhaust temperatures stabilized at 1,050 degrees Fahrenheit. Oil pressure held at 95 psi. During the taxi run, engineers monitored cylinder head temperatures through analog gauges mounted on a temporary panel. Readings varied between 370 and 410 degrees Fahrenheit, within expected tolerances. The engine maintained full power for 7 continuous minutes without cooling interruption. Chief Test Pilot Bob Miner conducted the first liftoff at 10:27 a.m. The takeoff roll covered 1,100 feet. Climb rate averaged 2,800 feet per minute. The double Wasp maintained full throttle at 2,700 revolutions per minute. Above 8,000 feet, coolant recovery remained stable, demonstrating the air-cooled design's effectiveness under low-density air. At altitude, the aircraft registered 420 miles per hour in level flight. Manifold pressure remained at 52 inches of mercury. No vapor lock or detonation occurred. The observation team recorded all data on form for 92B for engine performance trials. Below the runway, Pratt & Whitney technicians continued to examine a spare cylinder assembly. The air-cooled fins were machined from forged aluminum, each less than 1/8 inch thick. The design allowed uniform heat dissipation across the combustion chamber. Earlier critics within the Army Materiel Command had declared such finning unreliable at sustained output beyond 1,700 horsepower. But on this day, the data showed otherwise. Engine vibration measured less than 0.05 inches per second at full load. Thermal stress distribution remained within design limits. No oil leakage appeared from the rocker housing after 20 minutes of flight. When the XP-47B landed at 10:54 a.m., its brake temperature reached 220 degrees Fahrenheit. The cowling showed uniform soot residue, a sign of stable combustion. The aircraft taxied to Hangar 2 for post-flight inspection. Observers noted the pilot's brief statement, "No overheating." Engine steady. Controls heavy. The note was entered into the daily flight log at 11:02 a.m. Photographers documented the event using speed graphic cameras with 4x 5-inch film. The resulting images later appeared in Republic's Technical Bulletin 47-TR3 under the title First Operational Evaluation, R2800 Installation, XP-47B. In the following hours, technicians removed the upper cowling and inspected all 18 cylinders. Carbon buildup was minimal. Exhaust ports remained intact. Valve stems showed no scoring. Compression ratios measured consistent across both banks. By the afternoon, Republic's chief engineer, Alexander Kartveli, reviewed the data. The engine's air-cooled system, once criticized as impractical for high-altitude fighters, had completed its first full-power flight without incident. The report concluded that the combination of the RO-2800 and the new airframe warranted further endurance testing. The next trial was scheduled for March 12, weather permitting. The observers left the airfield as the sun dropped below the horizon. The hangar lights remained on, illuminating the silver fuselage of the Thunderbolt prototype, silent but intact. By mid-1941, American aircraft designers faced a decisive engineering problem. Existing liquid-cooled engines such as the Allison V1710 and the Rolls-Royce Merlin offered high-altitude performance but suffered catastrophic damage from single bullet hits to their coolant systems. A punctured radiator or coolant line meant engine seizure within minutes. Loss rates in operational testing confirmed the vulnerability. At the same time, the U.S. Army Air Corps Technical Service Command required a long-range escort fighter capable of operating above 25,000 feet. Such performance demanded both power and endurance. Conventional wisdom favored inline liquid-cooled engines for aerodynamic efficiency. Yet field experience in Europe and China showed the opposite. Survivability was limited. Pratt Whitney engineers, under project manager Leonard Hobbs, proposed a radical alternative, the RV-2800 double Wasp. It was entirely air-cooled, eliminating radiators, pumps, and coolant lines. The engine used dual-row cylinders and direct-drive supercharging. The proposal was recorded in Company Memorandum P&W, ER 44-1939. At the time, the concept was regarded as impractical for high-speed fighters. Republic Aviation's lead designer, Alexander Kartveli, disagreed with the prevailing assessment. His design studies from late 1940 indicated that an air-cooled radial, though larger, could deliver equal or greater power with superior battlefield resilience. Early drawings, preserved in Republic File 47-1A, show oversized cowling sections accommodating the R2800's diameter of 52 inches. The fuselage cross-section was adjusted accordingly. Military evaluators raised objections. The aircraft would be heavy. The frontal area would increase drag. The landing gear must be lengthened. Command staff at Wright Field referred to the proposal as non-standard for pursuit classification. However, the rapid expansion of German air power and the heavy losses of British Spitfires in 1940 forced reconsideration. The RV-2800 itself represented a leap in material science. Each cylinder used forged steel barrels with aluminum alloy heads. Cooling fins were milled to a tolerance of 0.005 of an inch. Twin ignition systems ensured redundancy. The mechanical supercharger, driven at 6 times crankshaft speed, maintained sea-level manifold pressure up to 20,000 feet. These specifications were confirmed in the Pratt Whitney Engineering Report EU 216-41. When the United States entered the war in December 1941, procurement schedules accelerated. The Air Corps authorized Republic to build a prototype integrating the RA-2800 with a new high-capacity airframe. The order was formalized as Contract AC 27833 on September 6, 1942. The resulting aircraft received the designation XP-47B, the first Thunderbolt. The industrial infrastructure required to manufacture the RA-2800 was unprecedented. Pratt Whitney expanded its East Hartford facility with new forges, heat treatment plants, and precision grinding lines. Each engine required more than 5,000 individual components. Assembly time averaged 1,100 labor hours. By early 1943, monthly output exceeded 250 units. Meanwhile, combat intelligence from North Africa and the Pacific confirmed that radial engine aircraft such as the Grumman F-4F and F-6F sustained battle damage better than liquid-cooled designs. Reports from Guadalcanal noted aircraft returning with multiple cylinder hits yet maintaining power. The evidence supported Hobbs's argument that air cooling enhanced survivability without significant loss of efficiency. Within the U.S. Army Air Forces, General Henry Hap Arnold approved full testing of the double Wasp-powered P-47. The aircraft's weight, over 13,000 pounds, placed it beyond any prior fighter category. Nevertheless, the expectation was clear: high-altitude performance, dive capability, and resistance to enemy fire. By early 1943, the context for aerial warfare had shifted. Bomber formations required escort beyond 500 miles. The Luftwaffe's dominance over occupied Europe depended on interceptors that could climb rapidly but were fragile under sustained fire. The Thunderbolt, equipped with the R-2800, entered this environment as a test of American industrial and engineering doctrine. Every recorded evaluation emphasized the same question: could an oversized, air-cooled fighter outperform the sleek, liquid-cooled designs dominating Europe? The data would soon provide the answer. Testing of the XP-47B entered its second phase on March 12, 1943. Weather conditions were clear, visibility 10 miles. Air temperature measured 38 degrees Fahrenheit at field level. Republic's engineering staff recorded engine startup times, cylinder head temperatures, and supercharger boost data at 1-minute intervals. At 9:41 a.m., the double Wasp was advanced to military power, 2,700 revolutions per minute and 52 inches of manifold pressure. The aircraft accelerated to 180 miles per hour by the 1,000-foot marker. Takeoff time was 8 seconds shorter than the previous trial. Engine vibration remained negligible. Test reports indicated no overheating during the 25-minute climb to 30,000 feet. Cylinder head temperature averaged 392 degrees Fahrenheit, well below the maximum permissible 525. Oil temperature stabilized at 210. Carburetor air temperature was maintained at 110 through ducted airflow. The results exceeded Air Corps Specification 98-241A for altitude engine operation. At high altitude, the P-47's mechanical turbo-supercharger engaged automatically. Exhaust gases drove a centrifugal turbine producing an additional 6.5 pounds per square inch of boost. Airflow was routed through a duct system extending 20 feet to the rear fuselage. This feature, although mechanically complex, allowed the double Wasp to maintain full rated power at altitudes beyond 25,000 feet, a capability unmatched by contemporary designs. Ground engineers observed power transition smoothness during descent. No compressor surge or detonation occurred. Fuel consumption at cruising speed measured 160 gallons per hour. Endurance range was estimated at 800 miles with internal tanks. With drop tanks, range exceeded 1,200 miles. Concurrent durability trials began at Pratt Whitney's East Hartford facility. Engines were operated continuously at 2,000 horsepower for 150 hours without overhaul. Maintenance logs confirmed that only 3 components required replacement: 1 exhaust valve, 1 spark plug lead, and a magneto coupling. This was documented under Test Report E316-43. Army inspectors from Wright Field conducted ballistic resistance testing on a decommissioned cylinder assembly. Using standard .30-06 M2 armor-piercing ammunition at 100 yards, 5 rounds were fired at the fin area. 3 fins were destroyed, but compression remained sufficient for combustion. The cylinder continued operating for 42 minutes post-impact. Cooling performance declined by only 4%. Flight results at Republic reinforced this evidence. During the 14th test sortie, 1 aircraft suffered a fractured oil line from vibration. The pilot completed a 12-minute flight and landed safely. Post-flight inspection showed oil loss of 3.5 gallons but no seizure. Engineers attributed this to the double Wasp's ability to shed heat through direct air exposure rather than fluid cooling circuits. In parallel, comparative studies were performed against the Allison VR1710 engine used in the P-38 Lightning. Under identical test conditions at 25,000 feet, the RI-2800 maintained 1,980 horsepower, the VR1710 produced 1,430. Mechanical reliability per hour of operation was recorded at 97.2% for the RI-2800 versus 88.4% for the liquid-cooled model. Reports circulated through the Material Command describing the new power plant as overbuilt but unbreakable. Engineers noted that the engine's 2,360-pound weight was offset by its structural simplicity. No radiators, pumps, or glycol systems were required. Field maintenance time was reduced by 27% compared to liquid-cooled equivalents. In April 1943, the first production P-47BS were delivered to the 56th Fighter Group at Bridgeport, Connecticut. Ground crews logged early maintenance feedback. Sergeant Frank Devine recorded that engine runs rough if cold started below 30 degrees Fahrenheit, otherwise steady at all RPM. The note appeared in the group's maintenance summary number 6. The operational evaluation flights revealed another discovery: the aircraft could absorb extensive damage and remain flyable. One test unit returned after losing a full cylinder due to detonation failure, yet power output remained above 1,200 horsepower. The pilot reported normal control during descent and landing. The findings were verified by Republic engineers on May 2. These tests marked the transition from experimental validation to tactical proof. The RI-2800 had demonstrated that a well-engineered air-cooled radial could deliver the performance of liquid-cooled engines while surviving battlefield punishment far beyond expected limits. By mid-May, the Thunderbolt's reputation within the Army Air Forces shifted from skepticism to measured confidence. The data no longer represented a theoretical advantage, it was empirical evidence that toughness could be engineered, cylinder by cylinder. By June 1943, combat deployment of the P-47 Thunderbolt began across the European theatre of operations. The 56th Fighter Group, stationed at RAF Kingscliff, England, recorded the first sorties against German air defences. Pilots reported that enemy fighters, particularly the Bf-109G and FW-190A, were faster in climb but less durable under sustained engagement. Operational debriefs from the 62nd Fighter Squadron noted consistent engine reliability even after long-range escort missions exceeding 5 hours. Cylinder head temperatures rarely exceeded 450 degrees Fahrenheit. Supercharger boost remained stable at altitude, confirming that the R-2800's air cooling system required no liquid regulation and no additional weight. On July 30, 1943, a Thunderbolt returned to base with over 100 visible bullet holes. The aircraft's oil system was damaged, and one cylinder was completely destroyed. Despite this, the pilot landed safely at Boxted Airfield. Inspection confirmed that 17 of 18 cylinders continued operating. The double Wasp maintained power until full shutdown. The event was recorded in the 8th Air Force Technical Intelligence Bulletin number 64 as an engine operation under battle damage. This and similar incidents reshaped engineering assessments. The double Wasp cylinder design, with individual fin separation and redundant ignition, allowed partial functionality even under direct impact. No single projectile could disable the engine's entire cooling system, a fatal flaw of liquid-cooled engines, whose radiators and pumps were single points of failure. Maintenance officers issued comparative readiness reports. During June through September 1943, P-47 squadrons maintained an average serviceability rate of 89%. Comparable P-38 units averaged 73%. The improvement was attributed to reduced engine maintenance requirements and resistance to coolant-related malfunctions. Factory data from Pratt & Whitney confirmed minimal overhaul needs. Average time between major service intervals was 350 flight hours, nearly double that of other contemporary engines. Only 3% of engines required replacement during their first 200 hours of service. The strategic realization followed quickly. For the first time, an American fighter could match European interceptors in power while surviving damage that would destroy most aircraft. The Thunderbolt's mass and air-cooled design produced a margin of safety that altered pilot confidence and mission tactics. Reports from the 8th Air Force noted that P-47 pilots frequently returned from escort missions with severe structural and engine damage yet no fatalities. The aircraft could lose cylinders, propeller blades, or partial cowl panels and continue flight. This reliability built operational doctrine around aggressive engagement and deep penetration escort, missions previously impossible for fragile designs. Technicians at Republic's Farmingdale plant received steady feedback from field units. Adjustments were minimal: improved intercooler ducts, reinforced cowling joints, and thicker exhaust manifolds. The core engine required no redesign. Each field modification was recorded in Technical Order 01-65 BC-2. In August 1943, General Arnold's headquarters issued an internal directive citing the Thunderbolts demonstrated combat survivability derived from mechanical resilience of the I-2800 installation. The wording was factual and brief but marked official acknowledgement that the air-cooled system had surpassed expectations. Further statistical summaries confirmed the trend. During the second half of 1943, the 56th Fighter Group recorded an engine failure loss rate of 0.1 for per 1,000 flight hours. Comparable rates for Allison and Merlin-powered aircraft exceeded 0.7. From a strategic perspective, this difference translated directly into aircraft availability, sortie frequency, and pilot survival. The R-2800 had not merely improved performance, it had changed operational endurance. As the year closed, technical officers concluded that the crazy and engineer's air-cooled concept, once dismissed as unsuitable for high-performance aircraft, was now the foundation of America's heaviest and most durable fighter. The realization was simple and measurable: durability was no longer an accident of design, it was engineered into every cylinder of the double Wasp. By early 1944, large-scale production of the I-2800 double Wasp reached full wartime output. Pratt & Whitney operated plants in East Hartford and Kansas City. Combined monthly production exceeded 2,000 engines. Each was individually tested for 50 hours before shipment. The engines powered not only the P-47 Thunderbolt but also the F-6F Hellcat, F-4U Corsair, and later the A-26 Invader. Industrial records from the War Production Board show that by March 1944, nearly 1 out of every 5 American combat aircraft used a variant of the I-2800. This concentration simplified logistics and standardized maintenance procedures across multiple aircraft types. Engine components, from ignition systems to cylinder heads, were interchangeable among platforms. Strategically, this commonality provided the U.S. Army Air Forces with a logistical advantage unmatched by the Axis powers. German aircraft production relied on numerous engine models: the Daimler-Benz DB601, BMW 801, and Junkers Jumo series, each requiring distinct parts, tooling, and service training. American factories, by contrast, concentrated on volume and interchangeability. Statistical summaries from the Combined Intelligence Objectives Subcommittee later confirmed that Allied engine production rates exceeded Germany's by a factor of 4. The R-2800, though complex, was designed for assembly line manufacturing. Forged steel barrels, pre-fitted pistons, and modular accessory drives reduced manual fitting. A trained technician could assemble one complete cylinder assembly in less than 40 minutes. The double Wasp's success influenced aircraft tactics as well. P-47 units adopted low-altitude rhubarb strikes against transportation and industrial targets in occupied France. Engine reliability under sustained low-level power enabled continuous high-speed operation without overheating. Fuel consumption rose sharply, but performance remained stable. Post-mission data logs recorded consistent oil pressure and normal head temperatures even after multiple strafing passes. In the Pacific Theater, the same engine powered the Navy's F-6F Hellcat. Reports from carrier air groups during the Marianas campaign noted similar resilience. Aircraft frequently returned to decks with extensive wing and cowling damage yet operational engines. Navy maintenance crews described the double Wasp as tolerant of neglect, a term appearing in Bureau of Aeronautics Maintenance Circular 14-44. The scale of our 2800 deployment prompted infrastructure adjustments. Pratt Whitney established mobile overhaul depots in the United Kingdom and Pacific Islands. Each depot could rebuild 50 engines per month using prefabricated sub-assemblies. Field replacements required only 2 days of work. This minimized downtime and kept operational strength high during peak operations in mid-1944. From an industrial perspective, the R-2800 represented the culmination of pre-war American mechanical design principles, redundancy, overbuilding, and standardization. Its two-row radial configuration, though bulky, provided unmatched damage tolerance. Cylinders operated independently, each receiving airflow directly rather than through shared coolant circuits. Data from the Army Air Forces Materiel Command showed that the mean time between unserviceable conditions exceeded 400 hours by late 1944. Average overhaul costs were 18% lower than for liquid-cooled engines of equivalent output. Spare parts logistics were simplified through centralized production contracts managed under Procurement Directive PD 3217. The Thunderbolt itself evolved accordingly. Later models, notably the P-47D and P-47M, integrated uprated versions of the R-2800 with improved superchargers and intercoolers. The aircraft's combat radius extended to over 900 miles. With external tanks, missions to Berlin became feasible. German intercept reports from 1944 frequently mentioned the Thunderbolt's survivability. Intelligence files from the Luftwaffe's Jagdgeschwader 26 referred to it as the Der Panzerjäger, the tank-like fighter. Attempts to destroy it with short bursts of 20 mm cannon fire proved ineffective. Engine failures caused by enemy hits were statistically rare. At a strategic level, the R-2800 demonstrated how engineering decisions could translate directly into combat endurance. What began as an unconventional air-cooled experiment had become an industrial backbone. By standardizing design and maximizing durability, the United States achieved continuous air superiority through sheer operational persistence. By the end of 1944, over 100,000 double Wasp engines had been produced. Each one represented a precise balance of metallurgy, airflow, and practical wartime necessity. The results were visible across 2 oceans, fighters that kept flying, missions that returned, and an air campaign that no longer depended on luck. When hostilities ended in August 1945, the R-2800 double Wasp had accumulated over 200 million combined flight hours. It powered aircraft in every major theater of operations: Europe, the Pacific, North Africa, and China. No other piston engine of the war matched its total operational record. Post-war technical evaluations at Wright Field confirmed the engine's performance data. Test engine number 2800-18W, with 412 combat hours logged in a P-47D, was disassembled for inspection. Cylinder bores remained within tolerance. Bearings showed uniform wear. Compression loss averaged less than 5%. Investigators concluded that the air-cooled design provided superior long-term integrity under extreme duty cycles. Statistical summaries from the Air Materiel Command in 1946 listed the AR-2800's mean time between failures at 472 hours, a record figure for a wartime piston engine. The closest equivalent, the Merlin 66, averaged 289. Maintenance man-hours per flight hour were 1.7, compared to 3.2 for liquid-cooled types. American engineers later cited the double Wasp as the transitional design between piston and jet propulsion. Its supercharging systems, intercooler arrangements, and high-altitude performance directly influenced early jet engine compressor configurations. Declassified memoranda from the National Advisory Committee for Aeronautics, NACA Report 1387, referenced the AR-2800's thermodynamic efficiency as a baseline for turbine development studies conducted in 1946 to 1947. In operational histories, the Thunderbolt survival rate remained unmatched. Combat loss data compiled by the 8th Air Force showed only 0.7% of P-47s lost to engine failure. In contrast, P-51 units reported 3.2%. The difference was entirely attributable to the absence of coolant systems and the double Wasp's ability to sustain damage while continuing to produce power. For pilots, the engine's dependability translated directly into survival. After-action reports frequently contain short, factual notes, returned on 15 cylinders. Oil line shot out, engine held. Cylinder head punctured, still running. These were not extraordinary cases, they were routine operational records. Post-war production continued for several years. Civil variants powered transports, fire bombers, and research aircraft. Pratt and Whitney maintained a continuous production line through 1957. Many engines remained in service into the 1960s. Engineering assessments conducted decades later identified the AR-2800 as one of the most balanced mechanical systems ever built for aviation. Its combination of power, simplicity, and field resilience exemplified mid-century American manufacturing at full wartime efficiency. No element was decorative, every part served function and endurance. In retrospective analysis, the skepticism that greeted the double Wasp in 1939 appeared unfounded. The same principles that critics labeled overbuilt or inefficient had produced an engine that defined mechanical survivability in combat. When later turbine engines adopted redundant systems and simplified maintenance procedures, engineers credited the AR-2800 as their conceptual precedent. By the 1950s, the U.S. Air Force and Navy archives classified the AR-2800 as fully obsolescent but historically exemplary. The phrase appeared in Technical Summary T-47-50. It captured the paradox of its legacy, outdated by technology, yet unmatched in reliability. Today, preserved P-47s, F for us, and F-6FS still operate with original AR-2800 engines. Many have surpassed 1,000 total hours without major overhaul. The metallic rhythm that began at Republic's Airfield in 1943 continues in museum hangars and airshows worldwide. Measured by endurance, not innovation, the AR-2800 proved that engineering conservatism, air instead of coolant, weight instead of fragility, could win wars as effectively as firepower. The double Wasp's legacy endures not as a relic of machinery, but as data, empirical proof that durability, when engineered with precision, becomes a strategic weapon.